Thank you. This is sort of a continuation. So at the Annenberg Center, I jumped to one slide with math, and now this is going to be 2 hours to explain that one slide. That's pretty much what it is. And I really want to emphasize that we are coming from diverse scientific backgrounds, and the language barrier is actually bigger than you probably think. So what I'm going to do, I take my mission, my mission is to take someone with a background in PDE and maybe a little bit of understanding of probability and statistical mechanics, a little vague one, and through the process of going from a n-particle, basically molecular dynamics model. So I would say Jörg talked quite a bit about here. And when I say atomistic, I should really say atomistic with electronic DFT, not ab initio with full electronic resolution. And then there's traditionally another step where you sort of coarse grain something like this, and you get molecular dynamics, right? Molecular dynamics is coarse grained. You get average sort of potentials, and Mauro would look at this and say, how do we find these average potentials? But then there's three other limits that you can sort of do. This is not really a limit. You can reformulate it now in a completely probabilistic sort of statement, which is sort of like the wave function over in the atomistic. But there's a very strong limit, a very strong map between electronic DFT and the BBGKY. And so you do a probabilistic format, which gives you an enormous PDE in a huge number of variables. And then you can take marginals of this and get a upper triangular, if you will, system of PDEs. And you would hope that maybe the bottom one is the most important one and everything else is just copies of it in some tensor product space. And if that's true, then you get to a Vlasov equation in the mean field limit as your number of particles, say, goes to infinity with certain assumptions on scaling and structure of your problem. There are some theorems in that direction. And then you take a hydrodynamic limit, which is merely, literally just integrating out what you might call the microscopic variables, the things you don't care about. I don't really care about the individual velocity of the particles, so I'll just integrate that out. What I care about is maybe positions and densities and more macroscopic things. So you integrate out a certain family of these. And so what I'm going to do is I'm going to step you through in a sort of PDE language from here to here to here to here. And then I'll do it in a sort of general way. And then I'm going to do it for a very specific system for a collection of dipoles, sometimes called the Stockmeyer model, which would then give you a continuum model. At the end of this, you get sort of continuum models. But it'll have two time scales, and I'll really emphasize why it doesn't fit so beautifully in the mean field limit. The scaling for the mean field limit kind of assumes, in some sense, that you really have one dominant sort of time scale scaling for the time. And when you have multiple ones, you could probably make it work, but it becomes a little bit more tricky. OK, so I'm going to step you through it. Again, I am trying to pitch this at a level of a sort of graduate student or I don't know, postdoc, young faculty with a PDE background and trying to get you up to speed with the notation. So when Jörg says something, you go, OK, well, I kind of vaguely remember. But there is a little bit of notation that you cannot avoid, I find. But I did find this very, very interesting to go because there's sort of two. Should I go back to the slide? Well, I think I skipped a slide. I want to go. Yeah, so really there's I put a bunch of right on the slide last time, but I missed this part at the top. There's sort of, this is very common in statistical mechanics. This is like, bread and butter. And I find the statistical mechanics literature to be, from my perspective, notationally terse with certain numbers of cognitive jumps that I just cannot fill back in, right? So it's like, Jörg was up here today, and he had the wave function phi and the density n, and they're coupled, and he knows they're coupled. But I'm looking at that, I'm like, I think those are coupled. Aren't those coupled? And Dima said, aren't those coupled? Yeah, Dima, thank you. Exactly. Because it's just so obvious, and there's just so much of it just gets pushed on. There's so much, and it gets pushed under the rug. And so I find the cognitive jumps make it hard to read the papers unless you go back to the textbooks, which is just too much work for me. There's a probabilistic framework, and there's an excellent text. I'll have a reference to it by Francois. What's his last name? Anyway, where's Adam? Is Adam here? Okay, I think what was it? Gauss. It's a very nice introduction to this, but it's very probabilistic. And there's a lot of notation. So now all the notation is out there in front for you. But in some sense, are there really so many details? Do I have to wait? The notation becomes like a thicket. So if you're not a probabilist, that's also, I find, to be a heavy lift. And so what I did is I went through all this, and I rewrote it in what I would consider a PDE sort of framework, eliminating as much as I needed. And it really sort of, I took a lot of inspiration from Tadmore's papers. I find him to be an excellent writer. If you have to get from point A to this idea, what is the least amount of notation you have to introduce? Once you know all the options, and you read Tadmore's paper, you go, oh, that was ballet. He is balletic about getting from point A to point B without introducing a single unnecessary idea. So I tried, but I couldn't follow him exactly because I wanted to go a different place than where most of the places you go. But OK, I'm going to try and avoid as much notation as possible, but there is still some notation. So, and I'm going to make a couple of distinctions, right? I think Jorg mentioned this before. There are trajectories and there are variables, and I'm going to give them different names. So you have n identical particles. I'm really thinking of this. I'm starting with a molecular dynamics simulation. I've taken out all of the electrons. I just have a molecule here and a molecule there, and they're interacting with each other pairwise. N identical particles, capital X bar is their collection of positions. So I have, maybe these are in RD, so I've got n RD. They have velocities, each in RD, so little VI bar is in RD. And these are time traces. These are like little paths in this 2D n-dimensional space. So you take X and V together. And you put down a Hamiltonian. This is sort of where molecular dynamics starts. I'll give you a simple interaction law, depending upon the differences, the distance between, the norm of the distance between any two particles, and their velocity. I scale all the masses to be equal. And there's an interesting 1 over n out there. And this is one of the scalings that you do in the mean field limit. And I'll get back to this. What is the, how general is that? If I do a Hamiltonian flow on this, that means I want a flow that preserves this energy. Then the canonical Hamiltonian flow is just that the time derivative position is velocity, and the time derivative velocity is the force. So I've got this sort of sum of two particle pairwise forces acting on each particle. And the force is just the gradient of this part of the energy, and so you get x over x bar. That's the x gradient of this guy. It's the x gradient of the energy. So capital F notation. Roman E is the energy. Roman F with no subscript is the scalar force. That's a vector force in RD. OK, and so let's put all our variables together. I got Zi bar. These are traces, time-dependent traces. Xi, Vi, and capital Z bar is this huge family of them. And so you could think of this system sitting in this sort of framework. It's a beautiful Hamiltonian skew. Z bar is the skew acting on the gradient of some Hamiltonian. And that's the classic formula for a Hamiltonian system. So this is nothing other than Hamiltonian dynamics. I got particles flowing around, conserving total energy, and run into each other. And it could be a mess. It's a big, big system, and you wouldn't ever want to have to solve it.
Please, can I ask a quick question?
Yeah.
Are you requiring that pairwise interaction for linear stuff, the simpler force expression, or is it
I am requiring pairwise interaction in order to minimize notation, but there's nothing. There's several assumptions I'm making. Yeah. You're right. It doesn't have to be pairwise, and there's something that comes. But I do want to. So there's a point where this is exactly. I'll show you where pairwise comes up in a. It was very odd. I have to say, it was extremely odd to do this exercise, and it took me a solid week of only doing, not a week of, I was doing it for a week, doing it only every day for a week. To really, how do you rewrite this in a PDF form? It wasn't obvious to me at all. I made a lot of mistakes, and they're very, very, very learning mistakes for me. You know, we had read Gaussian, and I thought I understood it, and then I realized I didn't understand a thing.
A question related to that. I mean, if it's not only a function of pairwise distance, do you still need the force to be the gradient of an energy, which becomes a harder requirement if you have more than...
I wanted to fit into this framework, so I have to think about that question. If I have a 3-particle or a more complicated energy, I want it to be Hamiltonian, so I'll give you exercise right as a Hamiltonian. So if it's 3-particle, what does the Hamiltonian look like?
Fine, well.
Yeah, it should be fine. It should be fine.
It's really good. So now you can really go to gradient is always right thing.
Doesn't change much. It doesn't change much. But there are some very interesting questions that come out exactly out of this, and I do want to. And I made up some new notation because I think things deserve names. And there's so many things that don't get names. Okay, so it's on the right side, I'm a probabilistic interpretation of this. So now I'm going to go to a probability density F capital N on the huge space, R2dn plus 1. One is time, 2dn is the space variables, and it just maps me into a positive number. So at each point, it gives me the probability that in this huge space, and this is very hard to think about if you really aren't used to it, in a huge dimensional space, the probability that a particle is in a sort of box, right? So the probability that this particle at this time, this is a single particle, is in this box is just the integral of that guy, right? That's the classic probability density guy. Okay, but there's a lot of variables in there. It's very typical to say, oh, let's define an empirical measure, which is the average. So like, let's put a bunch of delta functions, but this is not what we want to solve. This is a different beast. These are delta functions on the small variables. This is a delta function on R2D. This tells me in this space velocity, three-dimensional space, three-dimensional velocity, what's the probability there's a particle here with this speed? Now you're going to say 0 because uncertainty principle, but I'm not into quantum mechanics, so there could actually be a particle. And then you add them all up and then divide by n, and you can get pretty much any measure you want. This is a sort of thing. This isn't what we're studying. What we want to study is this beast, and we want to think of this beast. And this is exactly, you already had this picture where he had Gauss's, and he did a 1 tensor approximation of Gauss, and then a sum of 8 tensor approximations. Exactly, this is exactly, but I think it's worth looking at this statement for a while because it is very easy. I confused myself many times not really realizing that these guys are the same thing, that this is how you write them. The tensor product of n low-dimensional delta functions, that means delta function at zi on space, whatever, L2 of xi, the ith coordinate. This tensor product is really a product of delta functions in the huge dimensional space with 0, 0, 0, zi, which is just the delta function at this huge coordinate. So this is sort of, this notation really means a product of these low-dimensional delta functions extended out, like vectorized like this. It's kind of obvious, but if you're not looking for it, it's very easy to confuse yourself as a PDE person. I found this line, and these slides I think will be online. If you want to go back and look at them, you can. Where'd that come from? Okay, guess that's been there the whole time. So it took me quite a while to I made a lot of mistakes not really thinking about that. Okay, how do I recover the ODE flow from the probability density?
I'm confused. When you're on the previous slide, what are all those zeros corresponding to here?
This is a vector in R2D. This is a vector in R2dn. Exactly.
So this is all different times, the other zeros?
No, these are, I have capital N particles. This is like an operator. Yeah. And you could say, what's the delta function? It's all the mass is located at zi, and I'm in a 6-dimensional space. This is all the mass is, this is now a R2dn dimensional space. And I've got all the mass, no mass in the first 6, no mass in the second 6, no mass, some mass here, mass is here, no mass there.
What about T? That's just confusing. It shouldn't be there.
What?
T should not be there.
So the T could be there.
Oh, what's T? I'm sorry. Oh, I'm sorry. T. What's T? Oh, T is a typo. Yeah. T is. I love transposes. Not no.
Yeah, it's transpose maybe.
Sorry. T. Thank you much. T is. I'm sorry. Yeah, it could be time dependent, but yeah. Now I get it. Yeah. I'm suppressing time T almost everywhere. Okay. I think that's, no, okay, how do I go to the next slide? What did I do? Now I'm doing something really weird. Okay.
It's, I guess, the same like a product ansatz that we're having then for, and here you have a delta function. In quantum mechanics, you would have then the single particle wave function. And then it's the same object. Or so you're really picking out then always one particle. That's your I, and then you are making the product over all these individual ones. Because we are really going down then to a single point, because it's a classical mechanics, it would be then like the delta function.
Okay.
That would be my interpretation.
Okay. Yeah, what I'm trying to do is talk to PD people. And so if PD people don't get it, then this is okay.
It's not exactly right, of course.
Okay, so there's an error in there. Okay, well then that's even harder.
Because I mean, if you want to say it's just a delta at some capital Z, it's not really a direct product of those partials. Because look at the action, right?
If I integrate all these, don't I get f at z1? Maybe, oh, these are not the same thing.
That is actually correct. The tensor product is correct.
Okay, oh, this one is not correct.
But this one is not.
I had to think about that for a
Because
second.
you are evaluating basically. I mean, you're
When I do
taking
it,
product, product of measures that all live on this big state space.
Yeah, so now I do an integral over all the two ND variables.
The tensor product makes sense.
Yeah. This one, okay, I'll think about it later. Anyway, point is, it's confusing. Okay, let's come back. Okay, let's look at let's rewrite the ODE in terms of the probability density. And so the way to think about it is I take the probability density and I project it against a fixed function, which is the function vi. That is not an unknown, it's integration against variable vi dvi. So this dz has all the variables in it. So the xi variable is just the projection of the probability density against a weight. The evolution of the velocities is the projection of the end particle density against this interesting weight here, which comes from the force field, which I'll call F sub I. It's the sum over all, you fix an I there. You sum over j not equal to I. So the I is fixed, you sum over the j. That depends upon the ith particle. And so this is a fixed function. There's nothing, this is completely known. This is the physics that you wrote down. This is how all the particles talk to each other. Okay, so you can verify directly. Let me just go through it. This one hopefully will work. That if I take my n, my probability measure to be a tensor product of n low-dimensional delta functions, then you plug it into here. You integrate out everything. Well, where you don't have an I, you get a 1. Now you integrate a delta function to get something that has no variable, you just get a 1. So you get 1, 2nd minus 1 times. And the one integral is not trivial, is the vi integral, because that's what I'm integrating against vi. And I integrate this guy, and I get vi bar. This is a dummy variable of integration, and that's my trace, right? That's the vi bar. So that's sort of the notation that I'm using. These are my time traces. This is my dummy variables of integration without the bar on top. How does this guy evolve? If v is of this form, well, you integrate it all up, and the only integrals that are of interest are the dxi and the dxj, where you sum over j, and you sum that back all up, and you get bars here, because now the delta functions replace these dummy variables with bars. You get 1 over n, and that's exactly fi bar at x. That's the force acting on f from all these other guys. But this is an interesting sort of beast. It's not quite a convolution, but it's sort of close.
Guess what you have now? It's really assuming a pair potential, or?
So here
Here at this place, so there's no way out, so because you have just, so this is pair potential.
this is pair potential, yeah.
So if we would go to something more realistic, so we would,
Yeah, okay, so this is interesting right here. This is exactly where pair potential sort of comes in for you. So let's just look at how does this act. How does, when I project fi on a product of tensor, a general tensor product. So let's just take functions gi. Gi is a function of xi and vi. Take its tensor product of separated variables, right? G1 is a function of x1 and v1. G2, x2, and v2. Right, you tensor product them up. What is this projection doing? What is this velocity doing? It's integrating out. I've got all these sums of this is the definition of fi. I've got all these g's, each one, integrated over everybody. When I integrate, what's interesting, if I pick a j, the interesting integrals are just the dxj and the dxi. So all the velocities run out. It's just the positions. Everything else gives me a 1. I get gxj bar and gij bar. Did I define the bar? The bar is the marginal of this guy. So you have to take the marginal, right? I've integrated out everything. This is gj bar is the marginal of gj. Right? I've integrated out everything else. So I guess it's because it's not it's okay. Okay, so these guys get convolved with this difference product, and that is a convolution. The blue part is exactly a convolution of GJ with F. F is the force field that's defined this guy. So it's a map into RD, and against GI. And so this is now you've taken this n tensor product and you write it as a sum of quadratic terms. These are now quadratic, and this is this is because you took a two-particle interaction. So the quadratic structure here in this projection comes from being two-particle interaction. You're just looking at particle I. You convolve particle J with all the force fields, and you project it onto GI, and that gives you the sort of basically the force. And so,
Cheese?
Yeah.
Could you extend it then to 3 particles, and then you would have then xi, xj, xk, and so on? So, because that's exactly what we would do then with machine learning potentials also, that we go into 3-body, 4-body, and so on, expansion, and you would immediately be able
But it doesn't
to
have the
extend
form of the minus, right?
yeah, this is a little bit. This is a. So now what you would do then is.
You would have then xi minus xj. So this is just a reference.
Yeah, well, it's the 3 bodies. What do you have? You have this. 3 bodies form a triangle.
Yeah.
3 bodies form a triangle, and so what?
It's not a convolution, right?
It won't be a convolution. It won't be a convolution. It won't be a convolution. But okay. All I'm trying to do is get people from a PD background through this thicket. And I agree, we can go all sorts of sides, but I'm just trying to get. But the point I'm trying to make here is that this tensor product is a hugely nonlinear step. This is really this tensor product going from G1, going from the space of all tensor products. Just give me a function G and do n tensors of the same function G, is a hugely nonlinear manifold, right? It's n linear. It's linear in each GI, but collectively it's nonlinear. And then I project it onto this pairwise interaction, and I get a sum of quadratic terms. But if I want to think about converging onto a tensor product space, the tensor product space is not flat at all. If G is small, n copies of G is very small. It's like G to the n. And if G is big, it's huge. So it really can blow up. If you tensor the same product, the same function many times, you get something huge. You want some of them to be almost 1 if you're going to tensor product them. So the space of n tensors is a very nonlinear space as n gets big. And so the idea of converging onto this sort of mean field, which is going to be a bunch of tensor products, is going to be very dependent upon where you are on this tensor product manifold. It's not flat at all. It's a very curved space. The curvatures are high. Yeah.
So the first equation, the second equality, so your tensor product equals to product. Will the dimension match?
The tensor product. This is a function of all the variables, and it's just so it's I hope I'm making this right. It's G1, so x1 v1, right? Those are my variables. So G of x and v is just this, right? I think. So it's a function it takes a scalar value, and it depends upon a whole bunch of variables. And so this is a scalar. That's a scalar. That's a scalar. Scalar value. And each of the components is just a product of it's like when you're doing separation variables when you find the eigenvalue problem for Laplace. Yeah, it's there's a lot of ways to get confused. And if you're familiar with this is incredibly low, slow steps, right? Okay, but this is interesting and worth thinking about. That what starts out linear, right? This is a linear map. I've got this fi as a fixed function I project on the Vn. It's linear, but this is highly nonlinear. And when I do this projection with this two-body thing, it folds out a quadratic part of it. If it weren't quadratic, this would be even more nonlinear. If it was 3 particles, you'd have to, and it wouldn't be convolution. But okay, it's enough, right? I mean, so okay. I think if you're a PD person, the first thing you want to do is sit down and work on a problem. Here's a problem, and I'll give you the backstory. It's an interesting backstory. It's a very nice backstory. Okay, so someone mentioned it to me when I was visiting in Illinois and said, hey, this is interesting. I never thought about this. Okay, so give me a function f in L2 of R2 plus. So I mean just the first quadrant. And if you can prove it, I'd be very interested in seeing it, because I have a partial proof, but I never actually worked out the whole thing, and I think it's true. So I've got, let's say, x1 and x2, And so this is my space. I'm in this quadrant here. And I give you a function f that's defined over here in this quadrant. And what you do with f, well, the first thing you do is a quarter plane radial average map. So you just go along the arcs of constant radius, and you average the function f over these arcs. It looks a little bit bad. I should draw them. Here's a, there's a radius r there, right? So I'm in the plane. I average it. I average f over an arc of radius r with respect to theta, 0 to pi over 2. And then, what do? Now I'm going to produce a map T that takes, some space, L infinity L1, back into L infinity L1 with mass 1. It takes G. G is a function only of one variable. So I'm going to give you G. Here's a function of R plus. G is some function like this. Hopefully it goes to 0 at infinity or something like that. I tensor product G with itself. So the function f that I'm taking this radial average of is a tensor product. So I take a tensor product, and then I radially average it, and then I normalize it so it has norm 1, so it has mass 1. And this is a strict contraction. I think it's strict contraction. I haven't actually proved that myself, but numerically it looks that way. And it converges to a unique fixed point, which is the Gaussian. So everything like this converges to a Gaussian. And so I looked at this for a while, and I worked on it, and I got a quick result. And then I was just to come to MSU. And the backstory is Peter Lax had just won the Abel Prize. And he was also giving the MSU colloquium because we had a Hungarian mathematician who was up for tenure that he was collaborating with, and so he thought he would juice the tenure case by going it. And he gave a talk, and we all got to talk to him. And I explained, I said, this is an interesting problem. I thought Peter would like this problem. And I explained it to him, and he listened very patiently for 5 or 10 minutes that I had. And so this is what I could show. And he said, OK. And he left. I said, OK. A week later, I got a letter. When he flown back, he worked on it on the airplane. I got a 4-page handwritten note where he recovered exactly everything I told him I had done, but not anything else. So OK. So Peter Lax on the airplane, he got close. It's an interesting problem. And it teaches you a lot. If you're a PD person, this is a good exercise to think about, to play with this map. You really understand better this tensor product structure. I found it to be very illuminating. Anyway, it's cute. And if you have a proof, I'd love to see it. And if you want, I'm sorry?
You need G or negative as domain of T.
Oh, geez, yeah. Yeah, do I need G? G, it better be mass 1 and positive. Yeah, I think you're right. G, it better be positive. Thank you, Mauro. Yeah, G positive. I didn't really get time to proofread all these as much as I wanted. OK, yeah, so G should be strictly positive, yeah. That's certainly enough. G is a probability density, yeah, I'm sorry. Sorry. L2R plus, yeah, G is probability density, exactly. OK, so now let's go through let's set up the BBGKY, and let's look at the convergence. And then I'm going to try and work it through. I'm going to try and explain to you how you would take the hydrodynamic limit even if you don't have the mean field. OK, so first of all, how do you get a PD? I think the simplest way to think of it as a PD person is that you have a flux, right? A flux gives you a conservation law. And so you have a probability density F capital N, and then there's a flux J that takes, this means things that are, I'm integrating against moments, so I like F maybe to be 0 at very high density. So F decays to 0 at infinity in velocity and position. Everything's localized. And so I want a flux J, and it's going to map it into a vector. It takes my function F, and it gives me the vector. And so the flux function is just the velocity. It's a huge vector. It's the velocities, but these are explicit functions. These force field functions, that's a huge vector, but only multiplied by Fn. So the dependence of Fn is just completely linear. It's a beautiful linear PD. That's a fixed constant vector. I just take this Fn multiplied by this huge constant vector, and that gives me my flux. You can, I was trying to model Gaussian, and you could, but I don't think it's helpful. You can group these together and call them Ks, and OK, I'm not even going to do that. So J is K. Call that vector capital K. It turned out it wasn't. I probably was going to delete that, but I didn't get time. OK, so if you want, then, you can write your flux, your PD. Once you have a flux, you have a conservation law. Katsu wrote down basically this conservation law. It's basically Green's theorem. Right? How does something evolve? You know the flux is. The time evolution, there's a time evolution, plus the divergence of the flux is my conservation law. So this is a hyperbolic PDE and 2ND plus 1 variables. This is the Liouville equation. And you can write it more. This is the form that we'd like to look at. OK. So now we'd like to understand how could we approach this guy, and the BBGKY hierarchy is to look at the moments of this, the marginals, I'm sorry. Okay, so first assumption is the particles are interchangeable, which is a little bit subtle. It means they're all identical, but also that the probability distribution is invariant under permutation of the independent variables. And you can show in the context that we have that if you start on the space of permutation independent variables, it's forward invariant, you'll stay on it. So that's a reasonable assumption at least.
Excuse me, can you define marginals?
Yeah, exactly, right here.
Okay.
I haven't quite got, yeah, exactly. So the J marginal of Fn, after I'm assuming it is permutation invariant, so I can change the variables and not change the integral. The order of integration doesn't matter. Then the jth marginal takes a much smaller space, 2dj plus 1 into r, because it's time dependent, and it's just the integrating out the variables higher than j. So I care where the first j particles are, but not the rest of them.
So essentially, from my memories from statistical mechanics, this is the n particles partition function.
This is the j particle partition function, not caring where particles j plus 1 to j to the n go. So independent. So what's the probability that the first 3 particles are here, here, and here, and the rest of the particles are anywhere? That's the idea. And this is a much smaller beast, and you really like this to have all the information in it that you want. And so correlation is the measure of the difference between the j marginal and the j tensor of the 1 marginal. So you take the 1 marginal, you take its j tensor, or you take the n marginal and integrate out and get the j, you get the n particle probability distribution function. Integrate out all these variables, you get this. This is a function of j variables. This is a function of j variables. How similar are they? If they're the same, then the particle distribution is uncorrelated. The particle positions are independent. That putting down 10 particles is like you have a single variable. You just pick it. You sample it 10 times and put them down. That's not the same. If they're correlated, you put 3 down. No, the 4th one depends on where you put the first 3. This is uncorrelated limit. And this is the idea you want to get to. You want to understand, will we converge to, as n goes to infinity, do these tensor products, are these the dominant sort of behaviors of the solution? And sometimes yes, and sometimes no. So let me go through the marginal evolution. Is there a time here? I don't have no idea. 2:36. Okay. So let's just write this down. I've got my Liouville equation for this incredibly large dimensional PDE. I've got this Fi of x, and I've got Vi, these are my fluxes, and I have my hyperbolic PDE. I'm going to drop this red term because it just clutters everything up. It makes the slides longer, and it doesn't do anything fun. So I'm just going to drop it, and then at the end I'll add it back in. I'm only going to focus on the blue term. And again, this is where the 2-particle nature of it is extremely important, because you're going to get what I call this 2-particle correlation thing. So multiply the n particles by a test function to get a weak formulation. That's 0 infinity, because I want to integrate by parts, and I have these weighted things I'm integrating against. And integrate by parts in Z1. You get a time derivative phi is independent of time, so the time derivative of this projection is equal to this sort of this F1 dotted with the gradient goes over here. There's a gradient here, V1, it goes on V. And then Fn phi is a function only of Z1, only of the first coordinate. Now, because we have interchangeability, we've got all these xj's, but I can switch them to zx2s. Any zj can be switched to a z2 because of interchangeability. And so I can rewrite these guys. This x minus phi j becomes x minus x2. And now I have an integration where I have a sum here, but there's no j's on the right-hand side. And so really the sum collapses down to an n minus 1. And yeah, n minus 1. And so what I have now is this sort of I'm back to this sort of pairwise interaction, this quadratic interaction, where one of the things is this test function. And so this is basically the reduction. This is the main idea of the reduction, that these guys simplify out quite a bit. Again, using very strongly the fact that this is a 2-particle interaction. Otherwise, it becomes much more complicated. Maybe not obvious, maybe not even obvious to extent. Okay, so after you collect this guy, you get n minus 1. This looks sort of like a convolution. I got grad v. This is just the weak formulation of this PDE, right? And phi is an arbitrary test function, smooth test function. This is exactly what you mean when you say I have a weak formulation of this PDE. So this is the sort of the evolution of the one marginal coupled to the two marginal. And so this is the generic framework that you get. These marginals couple in a nested sort of upper triangular sort of way. The jth marginal couples certainly to the j plus 1 marginal. That's the sort of new thing. Okay, so if you want to write it, I kind of find it appealing to write, let's just extend f to be f of z by making it independent. There's a velocity, add the velocities back in. So that x is in Rd. There's a velocity in Rd, but just don't worry about it. That makes the notation simpler. And then I can write this sort of as a what I call a 1-2 convolution. The 2-point convolution, very much motivated by the fact that f is a 2-particle interaction. So if you want to write this, you can write Fij of this 2-part convolution is the sum of this force field at Zi minus Zj. It's really like a convolution. F of z integrated over all these guys without Zi. So you basically take in particle Zi, you're fixing it, and you're integrating over all the Zij's to figure out the forces that they act. This is the sort of expression for the forces that comes out from this guy, this sort of 2-point. It's not a bad idea to give it a name. It's not a convolution. It's a more complicated n-1 dimensional integral of a convolution. And it gives you the sort of, in the more general framework, if you do the jth marginal, you get families that look like this. They're all coupled. It's upper triangular, but f and j only gets hit at the most by j plus 1. So you only couple to the one higher guy. And the idea is if you could maybe it doesn't matter after j gets to be super big. You think about correlation in water, probably the dominant structure is 5-10 particle correlation. Maybe that's all really that matters. When you get very high, maybe this doesn't have so much impact anymore. That's the intuition, is that you shouldn't really have to worry about the very high dimensional pieces of it, that the structure of the problem ought to be contained in the low dimensional, that's the hope, in the low dimensional correlations. Okay, and I did the wrong thing again, and I think I've got to go back over here now. Okay, hit the wrong button. Okay. Okay, so how do you get to a mean field reduction? So if the Liouville flow is indeed uncorrelated, then the jth marginal is exactly the tensor product of something. In fact, f would be the 1 marginal because that means the 1 marginal is f. So implicit in that is that the jth marginal is the n tensor of the 1 marginal. So in particular, when j is 2, Fn2 is just this tensor product of f of z1 times f of z2. That's how it depends on z1 and z2 in this product form. And when you take the limit as n goes to infinity, the 1 marginal equation, which has this term in it, this v1 gradient of Fn2, you can write down. Now you have, it's quadratic, it's nonlinear, right? So you get f here and f of x dot v dot. These are now dummy variables. The x2, v2 become dummy variables. In principle, here f is independent of v, and so this v prime integral is just a marginal, the velocity marginal of f, but it doesn't really matter. Okay, that's not really important what we're doing. But this becomes quadratic because tensor product is quadratic. It's the tensor product act that is nonlinear. That's where the nonlinear comes from, the tensor product. So you're projecting onto this highly curved tensor product space. And you can understand, as you go higher in the tensor product nomenclature, you're going to get more, you get stronger and stronger nonlinearities present in these systems. Okay, and if you want, you can write it as a convolution. So this sort of 2-point convolution on the tensor product space just becomes a classical convolution. And this is the Vlasov equation. The Vlasov equation is what's called the mean field limit. If, as n goes to infinity, you converge, all these marginals converge to tensor products, then you're solving this simple scalar, nonlinear now, because of the tensor product structure, PDE for this scalar density only on a few variables. And eventually I'm going to learn not to click that button. Okay. So there are large families of rigorous results. And I just want to give you one sort of caveat as to where they sort of sit, right? Okay, so this is now, I'm looking at Goltz's lecture notes, and here's the reference if you want to find them. I think they're an excellent write-up to the sort of some of the theory, actually introduce you to the theory from a probabilistic point of view, although there is some substantial lifting to get through the probability elements of it. So a couple of simple assumptions. One is basically Newton's second law that the force is equal and opposite. So you switch the two particles, the force goes the other way. That's not very big. The second is that the gradient of the forces are bounded. That is a very big assumption for this theorem. It can be lifted in some situations, but in general it's a little bit tricky. It basically says the forces are never singular, but all sorts of point reductions of forces, coulombs, force is singular when the particles are very close together. So it wouldn't solve that. Okay, then let's state this carefully. If some function f on the low-dimensional space solves the Vlasov system with initial data v0, and f sub n solves the full Liouville system with initial data that is the tensor product of initial data of this guy. So I take this small Vlasov system, and I take the initial data, and I tensor product up into this huge space. Then these guys converge. These guys converge as n goes to infinity. The n tensor product of something, this is a strange beast. You have to be very careful what you take a tensor product of n times. If f naught is big in some sense or small, really, that's a strong statement there. Okay, this converges weakly. Then these converge weakly as n goes to infinity. And I think the better statement is along this line here. It says that the n tensor, the jth marginal of this n guy, minus the jth tensor, is less than is not constant, 1 over n, e to the ct. It means the two solutions don't diverge. The exponential rate at which they diverge is bounded above. But there's a small coefficient out there. So it means on time, for fixed n, it means for time t looks like natural log of n, these will be reasonably close. Now, that's not the sort of result you want to base your life on. That's not, probably the truth is stronger than this, but it's very hard. It's very hard to prove a stronger result than this. Many results fit into this sort of category. What you would hope to prove, I don't know how to, okay, there you go. That's the way to get out. What would be more gratifying, what would make me feel more comfortable is if you could show that if I have enough particles, then there's constants, nu c delta bigger than 0, such that I have more particles than any initial data of the n particle that's close to an n particle tensor product. So I start close to this very strongly curved n tensor product manifold. Then the marginals converge. They get closer. If I start close, they'll get closer up to 1 over n. So if 1 over n is much smaller than delta, if I start close, I come in and I stay close. That's what you would hope is true. Then you could say I can replace the big problem with the small problem, and I'm clean. That's not known. I don't know any context where anything like that is known. So I just think we should be careful to say that the mean field limit is used broadly, and I think when I think of mean field limit, I think of this sort of result, but the proofs are actually a little bit weaker. The numerics sometimes feel like this, though. It often can look like that in some situations. Okay, so there are corrections to the mean field limit, and that's sort of where I want to go now. I sort of want to think about how can we use, if we don't have a mean field limit, is it an expansion in some ways? Could you get a convergent expansion? In some simple situations, you can. There's a recent paper by Mitya Drinks, 2021. So proving what's called the Bogolubov correction to the mean field. So assume basically the mean field limit holds. You've got Fn satisfies Liouville with tensor product initial data. You can define H1 and H2 by two evolution equations that are quite complicated. I'm not even going to write out what this operator is, LF. It's a whole other ball of wax. It's quite complicated, but you can show that this sort of system does a bit better. You get a 1 over n squared here. So 2 natural, out to time t, 2 natural log of n. Okay, but that's the sort of structure you're sitting with. It's not likely that you can rigorously improve on this, particularly not in a case where you don't have a mean field limit. There's not a lot of hope that you're going to push the theory here.
You expect that there's a nice 1 over n expansion for
I expect in this family that there is likely a 1 over n. I don't know. Now, I think they have constants here. I don't know how the you got to get the constants to behave. I don't know how the constants behave. I didn't play. There's constants that are independent of n, but there should be. Does C depend on on U2? C can be independent of n. C is independent of 2, but does C depend on n? No, no one's done that. For sure, no one's done that. Do I expect it? Yeah, it very much seems like this is a very, once these n tensor products are doing the right thing, you're really in a small, the set of functions f whose n tensor is reasonable are really very small. So you're really forcing the system onto a very small dimensional space. And so it's likely that you are very close in my mind. But I don't know. I'm not the...
What are the assumptions on F for this?
Well, this F. Well, he needs the mean field to hold. I was assuming they're very similar to what Gauss was doing, but I have a paper on my laptop and I could look it up, but I can't answer it off the top of my head. I think it's...
Is it up to Colonia? Sub-Colonia?
I don't know, and I'm not expert enough to have, understand which detail is sharp and not sharp. So I don't know. Roman, I don't know. And the best answer to that is I don't know, but I do know in my laptop, which I now have, thank you, that I can fix it. Okay. Okay, let me just talk a little bit about the scaling that appears in the mean field. How general is it? And it's fairly general if you really have one type of homogeneous interaction, right? So if you have a potential E that is long range, and so maybe the gradient of E looks like 1 over f to the p, like Coulomb, and you have n particles in a box of unit volume, then they have a separation, an average separation, n particles in a box looks like it's dimension n, or 1 over n in a box looks like 1 over n to the 1 over d, where d is your space dimension. It's kind of your average. So you expect f kind of scales like n to the p, the inverse power of that n to the p over d. That's sort of how f would scale as you put more and more particles in a fixed volume box. Okay, and so how can I make this into a homogeneous limit? You can rescale time, you can rescale space, and then the velocities rescale like this. And you can choose these guys. These will then, this is Galilean, this is invariant under this rescaling. There's a factor, a common factor that comes out, and you get a power of n to the gamma. And so if you look at the Vlasov or this sort of general system like this, you can always put an n to the gamma here. And there's a couple of sort of parameters, but they're really not that crucial. And so there's choices for alpha, the time rescaling, and the space rescaling, if p is reasonable. This choice of rescaling will give you the sort of 1 over n. But it really, really, really depends upon f being purely homogeneous. If f is not purely homogeneous, this mean field scaling is much harder to understand. So the mean field limit is a little bit special, and it comes up in many homogeneous cases with pairwise interaction, but it's a little bit special. Okay, so hydrodynamic limits. How do you take a hydrodynamic limit? It's relatively simple. If you have a Vlasov equation, and here I'm borrowing Tadmore's approach, you can define a density. You just integrate out the velocities. I have a function only of position and velocity now because I'm in a Vlasov system. Integrate out the velocities. I get a density rho, and I get a density weighted velocity u, so u rho, which is integrating out f times the moment v. So this is the projection of this density against 1, projection of density against the velocity. If you integrate the Vlasov with respect to dv, then you can get a evolution equation. You write this out, and you can compute these integrals. Right? I multiply by 1, and I integrate, and you get this sort of continuity equation. You get this. The density is convected by this. The average density, the density is convected by this sort of density-weighted average velocity. If you multiply the Vlasov equation by V and integrate, well, you get a VF up here. You integrate by parts here, you get a V tensor V. So when you integrate by parts, that's exactly where the Navier-Stokes sort of V tensor V comes from. The divergence of this guy and the V divergence of this convolution term with a V outside, these are all 0. And when you integrate them out, you integrate out the velocities, and you got to play one little trick. You can define, you can't close this, but you can define what's called a pressure. You can look at F times V minus the average velocity, tensor product V minus the average velocity. This is not F of, but F times. And you can expand this out, and you get a couple of terms which combine and cancel in the right way. And you get F V tensor V minus rho U tensor rho. So you can replace this term with a pressure plus rho U tensor U. So what you don't know is this sort of moment. This pressure is the sort of measure against the probability density of the velocity minus its average value. So it's the deviation of the velocity from its average value. It's the expectation of the velocity, or the deviation of the velocity from its average value. And so if you rewrite it as a convolution term, then you get F tensor rho rho, and you can rewrite the velocity equation as this sort of Eulerian evolution. What you have on the right-hand side is the pressure, well, on the left-hand side is the pressure term. So you get a pressure term over here that you don't know. But the rest of it closes. So now you've got a closed system. You just have to say, well, what sort of pressure law do I want? How does the velocity deviate from the average? And I think from the situations that we're interested in, the pressure term is not the dominant consideration. That it's relatively standard to take the pressure to be 0. Just assume you're on this sort of manifold where the velocities are all the average value. It doesn't change the underlying physics so much. So it can be important, but I don't think it's the crucial thing. What I think is crucial for us, and the last thing I want to do today, is to say, okay, what happens if we go direct to hydrodynamics from the BBGKY? What if we don't take a mean field limit, but we just say, okay, let's integrate out, let's take the BBGKY, and let's integrate out the velocity dependence. So I've got Vn3, which couples to Vn2, which couples to Vn1. And I'm going to take this system here, and I'm going to average it out. So I'll do a hydrodynamic limit here. And now I'll get a system over here, but it will include Vn2, and you can write it as Vn2 minus the tensor product of Vn1. And so this is this term is going to appear over here if you want to write it as perturbative. If you think you're not too far from a mean field limit, or at least you hope that, so let's introduce H2, this sort of two-particle correlation residual. This is a measure of distance to uncorrelated flow. Then the one marginal, if you rewrite it in this term, it satisfies Vlasov. You can throw in an external force if you want. It just sits right there. If you want to put in an external potential like an electric field or something, you can just throw it in like that. So you get Vlasov because I've basically subtracted out the two tensor and replaced the two marginal and replaced it with the two tensor. But then you get this extra term over here that you don't know. And if you want to view this as your stochastic terms, this is really where the system is fluctuating. It's an interesting question. If I integrate out the velocities, is that still a fluctuating variable? But certainly Vn2, I don't integrate out all the velocities. I integrate it with respect to Z2, but I don't integrate it with respect to Z1. So this is a sort of a more fluctuating term because I haven't integrated out the Z1 velocities out of here. And so this is more stochastic in that sense. It has more fluctuations. So generally, what people do in this approach is they define some sort of closure model. H2 is some function here, I'll reuse capital T, of the one marginal. That requires a lot of, guessing or insight or intuition or physical sort of behavior. And here I'm sort of copying a paper that Michael Murillo, I think, is going to talk about when it comes to workshop 1. So, okay. If we just take these, if we just go to this system now and we project it, we take the moments. So we integrate with respect to v1, with respect to integrate out the last remaining velocity, which is v1. And now I can define this density, this rho, and this pressure term. And again, let me go this way. What you get when you take this hydrodynamic limit, you get a term over here that's new. You get a correlation term. So here I just add an external force. It could have been there in the previous one. That's not new. What's new is this correlation term. And so correlation term, the correlation search term, if you have some information about what H2 is, if I know that there's some sort of stochastic structure, geez, what did I do? No, here you go. How, what, okay. No, oh, the laser, that's what I want. Okay, this one's a laser, sorry. If I have some information about what H2 is, then it belongs in here. It gets convolved against this two-particle guy. I plug it in here. I can rewrite it, in fact, in terms of ρ2. It's relatively standard, I guess, to write H2 in terms of ρ2, which is a marginal. It's the two-particle density residual. It's the velocity marginals of H2. All right, and so I put ρ2 here. I take this sort of two-particle convolution of this. The correlation force is this 1-2 particle correlation with this ρ2 density. And this could be a sort of ansatz for where the stochastic sort of terms come from. This is what's capturing, in some sense, this describes the variation, the fluctuation of this system about its mean field limit if the mean field limit is the dominant term. If this is perturbative, then this is sort of where you'd put, and he's not working anymore. This is where you'd put this perturbation term. It fits inside of this form. And if you want to learn what ρ2 is, then you have a box to put it in. You're not starting from no information. So particular, in a different context, sort of plasma physics, they sort of examine various closure models, and they're using exactly DFT and DFT and DD, dynamic density functional type ansatz. Crucially, they relate this two-particle density, ρ2, to the correlation function under a quasi-equilibrium assumption. And you can look at that, but it's a little bit outside my expertise, and I'm not willing to say anything about it. So that's where I'm going to stop.
Quick question. So these fluctuations, there's no time dependence, or so we don't know the frequency dependency. So this is getting lost. So
I've suppressed. So in all of these systems, all the functions are time dependent, and I have not written it out. So
okay, great.
So everything,
so it's not just
rho, u, every variable is time dependent, but there's too many variables, and
yes,
I suppress the time dependent. So that's suppressed. So yeah, this is very much time dependent.
The two-particle density is written with what it is.
Yeah.
Also time.
X1, X2, and then time, but suppressed because the page is only so wide. So yeah, so what I would say is, if you want to add stochasticity into this system, then it goes here. That's a good place to start. May go other places, but definitely, and that's not just random, it's sort of colored. I should have some idea about, I don't have to just make, okay, it's standard, you know, it may or may not be, it may be long tail, it may be something else, I don't quite know. But you could learn this, and you have a lot of data, I think, to try and understand. I'd say that's it's a framework in which to put this in. What I'm going to do in the next lecture is I'm going to go back through this, and I'm going to do it for the Stockmeyer model, and I will get these equations out explicitly, and they will have polarization moments in them. And you will see that you'll get two scales. If you have a particle with a mass, and it can spin because it's not round anymore, generally small particles, the angular momentum is much smaller than the mass, and so they spin quickly. They quickly go to equilibrium. You can have two time scales in the system immediately. One is for positions, and one is for rotational equilibrium. And so now you can say, well, there's a fast, and so there's an adiabatic submanifold, and now I could put in time-dependent forcing, and I could see frequency-dependent behavior, but the correlations would sit in there in a way that I know where to put them in at least. At least I have a physical model that says this is where I should put the correlations in. This is where I should put the noise in this correlation function. And I think that's so.
I think the transport term should be in divergence form there. It should be divergence of then rho u tensor u.
It should be like before. It should be like this guy, you say.
Yeah.
They're not the same, I guess. Maybe, yeah, if they're incompressible.
I mean, they're the same if you write the equation for the u itself, but...
I convinced myself that they were the same, but you're right. I don't remember anymore. So, yeah, it should be in this form. This is universal. Then this might be special. I don't know if I
mean, in that form, it appears if you just write the equation for u itself, u sub t. Then you have, like, Euler.
Yeah, okay, yeah, if I divide out by rho. Yeah, yeah. What did I do?
Otherwise, there is no density.
What did I do? Oh, I have a couple typos in there. Yeah, I don't know. At least one typo in that. I'm sorry. Yeah, this should have a row in it for sure. That's got a row. This does not have a row. I'm sorry. Sorry, I had meant to go over these more carefully, but instead I went out and had some nice wine in an Italian restaurant last night. So yeah, there's a typo there too. Thank you. Yeah. I'll try and correct that before we put it up. Okay, so, but that's what I meant with my slides yesterday. That now, if I put in this two particle marginal, then you get a term here. And this term here feels stochastic. It has structure, but it's stochastic. And maybe you could learn something about it. And then I'll try and say tomorrow, how would you set up a family of problems where you have polarization inside this guy, and try and be explicit about it. Okay, I'm done. Tomorrow?
So, what do you know about P? So,
the pressure.
It needs to be estimated too from that? Or?
Well, that's an excellent question. I would say, I would ask Roman, what do people do with the pressure term in general? So where did the pressure term, taking the pressure to be zero is not, they do it. There's all sorts of models for pressure, and no one quite knows. But that is the deviation of what's the word called? The variation of the pressure from its average value. And so, of the velocity from its average value. I would, in my intuition, that is not what is driving what's the right word? These energy fluctuations in this electrochemical system. I think, to me, in my head, it seems more plausible that it is the two particle, the second marginal, it's this term, which is more likely to cause big excursions. In particular, if I want to, can I go back to the back? How painful is that? If I want to go back to this slide, where I want to take this model and glue it physically next to this sort of model, what sort of information do I want to pass? I mean, the pressure could be interesting. That's like some deviation of the velocities, but it doesn't tell you even really, well, it tells you a little bit about the actual direction of the velocity. But I think you'd like to know something about the correlations that are going into there. And that's, well, I don't know. How do you glue these together? That's another hard question. I don't know. But this is, if I'm a PDE person, where would I start? Or I'm trying to do some sort of learning, then this is, I think, a relatively well-defined problem. Yeah, let me go back. I'm sorry. Whoa, okay, I went too far. Okay. Yeah, okay. No, up. Okay, sorry, this one. 26, yeah. I think this term, in my intuition, limited as it may be, is more likely to produce localization events. I don't think the deviation of velocities is really what's driving things. That's sort of not my intuition, but my intuition is maybe not worth a lot. I don't know. But, okay, our goal was to say, how could a mathematician begin to think about these problems? How could a PDE person begin to think about these problems? I think this is a framework where you can say, okay, what can we learn about this correlation function, this two-particle density residual? It's related to sort of observable. The correlation function is actually experimentally measurable, I believe. And so you have some various forms of way to get data about it. And so now you have a way to learn. And it's not huge. It's 6 variables maybe. Or no, in this case, 2D variables, where D could be 2. Could be 4-dimensional. It's not impossible. You could start in 1D, and there could be 2-dimensional function. OK, and it makes a problem that is tractable. And I think it could be helpful. Yeah?
Is the term that goes with the gradient of the pressure related to some dissipation?
Yeah, this is exactly, these are the forces. The way I understand the gradient of pressure is, these are basically the forces that are pushing you onto this. It's what's pushing the velocity towards sort of its average value. It's restoring the pressure. And well, OK, now I don't want to get too far over my skis, but I think of the pressure as the term which is keeping the velocity reasonably close to its average value. It's sort of keeping you on this sort of mean field limit. This is what's driving you. Hopefully, this is a restoring force. This is giving you, in a PDE framework, negatively Lyapunov things. It's driving you back onto this manifold of where the Vlasov equation is valid, but it's not dissipating energy. It's what I think of it doing is reducing. It's pushing you back onto this tensor product manifold, and so that's hopefully sort of like a spring. That's how I view it. Yeah, but people take closure models and they say this has some sort of relationship. There's various families of closure models, but I don't really know what physical intuition goes into these closure models. I'm not an expert in that. So and for this pressure closure, it's a different game. So this is one source. This is sort of one closure issue. What's the pressure?
You know why I asked this? Because I'm not sure I understood all the reasoning, but I know that you can derive exactly a generalized Langevin equation from the from the time evolution equation in terms of the Liouvillean. And so, since essentially this is a time evolution in terms of a Liouvillean, so I thought that I tried to find the similarities to.
You're looking for damping. You're looking for particle damping.
And so it's like, where is the damping? Where is the caging contribution to that? What is the?
Yeah, so you want to do like dissipative particle dynamics almost, or something like that. I don't think that's what this term is, but I'm not a.
Quick question. So for the last second question, the right-hand side, does it need to set the conservation law or not necessary?
This term.
Yeah.
What did I do here? This is a long time ago. This is, you write the convolution term. Yeah, probably actually. Yeah. yeah. Let's see. He should be in the same form as that guy up there. Yeah. Sorry. I was going through this. I was going to go through it last night, but okay, I didn't.
It's independent of V, so that's correct.
Oh yeah, because F's independent. Yeah, in this case, F's independent of V. That's right. Yeah. Okay. So that's right. In general, it doesn't make much difference. It does make a difference in this case. You're right. Here, it doesn't matter. Yeah. Okay. Yeah, because F's independent of V, and rho is independent of V. Okay. Yeah, I wrote these a while ago, and I don't have all the details. I didn't go over them last night. Sorry. Lost my laptop. Okay. Okay. Next time I will say here's a test problem. What I'll try to come up with is if I have a model which has dipole moments in it for the molecules, what comes out and what would the structure look like, and what are some test problems. But I don't know. I can't guarantee it'll be helpful. There's you're trying to build a bridge across a big river, and I'm rowing on one side, you're building on the other. And will they align when they meet? If they meet, that's a harder question. Okay, so that's what I got.